Welcome back to another MECH 1000 video. We're looking at Unit 10 in the Blueprint Reading textbook, and in the last video we left off talking about revisions. So we mentioned how in our mechanical drawings revisions are noted with a symbol here that has some sort of alphanumeric code in it that typically corresponds to some information in a table. So we can see here this particular drawing has two revisions, A1 and A2. So revision A, number 1, it used to be a diameter of 5 and now it's 0.75. And this dimension down here is now 1.25. It used to be only 0.75. So the fact that the number is underlined indicates that the dimension now is, or the drawing rather, is NTS, not to scale. So this is something that you would have seen a lot more of back in the days of hand-drawn ink and paper drawings. If you've taken the time to draw the drawing and then something about the design changes, it was not uncommon to change the text or annotation but leave the drawing alone. So even though this may still look like 0.75, and if you actually measured it with a scale ruler, you would see that it's 0.75. In reality, it's meant to be 1.25. So that underlining of the dimension means that the drawing is no longer to scale, and that rather than basing decisions or the design on the way it looks, you have to believe the text. And that's always the case. You should always trust the dimensions. Even if you, in our AutoCAD class, if you're following the dimensions from a drawing in the textbook and your drawing looks a little different what's in the book, as long as you follow those dimensions, then it's right, whether it looks the same or not. Okay, we talked about tapers before. We talked about how they're often described in TPF, the amount of taper per foot. Another way to show a conical taper is to use a symbol with a ratio, 0.2 to 1. So for every 1 unit over, it comes down 0.2. So that tells you what the taper is. Again, some material science information has come up in previous units, and I want to emphasize that this class is really just about reading and understanding the drawings. It's not a material science class. So a Rockwell hardness number is an example of type of information you may see on a drawing. It may be located in the title block or perhaps in a general note somewhere. We don't really need to understand all the details about what a Rockwell hardness number is. We basically just need to be able to recognize it on the drawing and read it for what it is. So the Rockwell hardness test is a test that is used for metals to determine how hard they are. And it gives them a certain number designation, and you may see that number on a drawing indicating what the material's Rockwell hardness number is. Another thing that I don't think we've talked about before, I think this is a new term, is knurling. So you've probably seen knurling before. You'll frequently see some type of knurl pattern on objects that need to have a good grip or reduce friction. So handles, tool handles, or barbell handles will often have a pattern. It could be a diamond pattern or maybe a series of parallel lines to increase the surface roughness and increase friction or grip. So this question, what style of knurling is specified? Here we see the knurling, here is the note, and we can see that it is diamond diamond knurl pattern is what's specified. What was the former dimension of the knurled portion? So this area here is what gets knurled. It's underlined. Okay, so that's an indication that this is not to scale. And the 1.75 has changed from what it was originally was. And if we look, it's revision A that changed it. So we go to A1, and we can see it was 1.5. So this may still be drawn as 1.5, but now the dimension has changed to let us know that it is now 1.75. So the former dimension was 1.5. Was the chamfer increased or decreased by revision A? So we need to find where the chamfer is. And there is a slight little chamfer right here and here. And we've got this revision A2 telling us the diameter of that hole now is somewhere between 1.5 and 1.5015. And if we look at this, actually, no, that's just telling us the diameter of the hole. That's not changing that chamfer. It looks like A3 changed the chamfer. Where is A3? Here we go, right up here. So we're talking about this big chamfer. This is the one that got changed by revision A3. 0.30 is what it is now. It used to be 0.44, so obviously it got smaller. How many bit changes have been made since this drawing was released? You could go around hunting for the revision symbols here, like, ooh, there's one, there's another one. But it's a lot easier just to look up here and see there are 3 of them. What is the overall height of this object? So we have this dimension here that takes us from this hole to the center of that hole. And then from this hole up to the top, we've got the 0.50 radius. And down here at the bottom, we have another 0.50 radius. So 0.5 and 0.5 is 1. 1 plus 1.75 is 2.75. What was the former height before revision? So this dimension here that we just used in the previous calculation was revised. If we look at revision A1, we can see that it used to be 2, which is 1/4 of an inch more. So it used to be 2 plus 0.5 plus 0.5. So it used to be 3. How many revisions have been made to the drawing? Again, the easiest place to look for that is in the revision table. 1, 2, 3, 3 revisions. What did revision C affect? Was gray iron. What is it now? Nodular iron. So it's affecting the material that the part is made out of. What was the former depth of the counterbore? So we can kind of guess that it is this. 0.12 is the former depth. But let's confirm that this revision is talking about the depth of the counterbore and not the depth of something else. Here we go, down here, revision B1. What kind of depth is it talking about? Yes, it is the counterbore. So the former depth, 0.12. Determine the dimension for letter F. All right, let's see, where is F? It's right there. This has a radius of 0.5, so double that radius gives us the width there of 1.00. Okay, and I always find this part of the blueprint reading book a bit humorous because I'm sure at one point in time, computer-aided drafting was something new, a new concept or a new idea. But this is very dated now, this information here. So obviously we know all about computer-aided drafting. That is part of this MECH 1000 course. We do both blueprint reading and computer-aided drafting. And I have had some students in the past with some manual drafting experience who like to try to tell me that manual drafting is better. And the only reason one might think that is because it's just what you're used to. They haven't had the opportunity to get accustomed to CAD drawings. But once they learn the software, I don't think there's any arguing that CAD drawings are superior. They can be much more easily edited, they can be duplicated, they're much more precise, and you can actually do things more quickly using CAD than you can by hand. And then again, I think this is kind of funny. Some of the technology pieces here. Cathode ray tube monitors. Boy, I can't tell you the last time I saw a tube monitor. That's very outdated. And what's interesting is I just recently saw some ads for the AutoCAD mobile app. So I can't quite yet envision a future where CAD drawings are done with a touch screen on a handheld device, but it is useful for perhaps reading drawings or viewing them. So the mouse and desktop computer setup is probably still going to be the best way to go about doing CAD drawings. And then here's another piece of outdated technology. Memory devices such as discs or magnetic tape. Oh my goodness, this is really old. So I've even seen in recent years students get away from using flash drives and opt for cloud storage. So these things are constantly changing with the technology. And as technology continues to get faster and the software continues to have more features, we're going to continue to see changes in computer-aided drafting. So as I was saying earlier, I don't think you can really make an argument in favor of manual drafting other than nostalgia. AutoCAD is faster, it's more accurate, it's neater, you can be more consistent, it's so much easier to make changes or revisions. Drawing storage, you can store an almost unlimited number of drawings to the cloud or in a small flash drive that fits in your pocket versus warehouses that would be needed to store the same number of hand-drawn drawings. If we were to look at this drawing and take a guess as to whether it was made by CAD or by hand, what would you guess? I would definitely say CAD, if for no other reason than the text. Hand-drawn drawings can usually be spotted by the text. Okay, let's talk about revisions again. Did revision A increase or decrease the diameter? We can see up here that it is now 6.516, and it was 6.5, so that's an increase. The last type of drawings I want to talk about are patent drawings. So when you file for a patent, which is a legal protection for some sort of invention or design, you need to submit drawings along with all the other paperwork that is usually prepared with a lawyer who specializes in patent law. And these drawings are a particular kind of drawings, a particular type. They need to show all the features of the invention, and they frequently include shading to give it an added sense of realism. So here are some examples of some patent drawings. They indicate the function of the object. They may indicate the material it's made of. It has to show all the details that highlight what makes this particular object unique. And as I said, it has this very recognizable shading that tells you that is definitely a patent drawing. So that's it for Unit 10. If you've got any questions, be sure to post them on the discussion board or let me know in class.